Hi there, welcome to Caltex Academy. Today on our board we have a nice question here on geometry. So there are three figures fused up together and we are asked to find the area of the shaded region. So if you're interested to see how these questions is solved, come closer and let's dive into the video. So here we need to have some few things defined. The first one, we need to get the area of the quarter cycle, and we can say A1 should be area of quarter cycle. So I can use just 1/4 to represent quarter. So we have that, and that is the mother geometry. Now next is A2. So let our A2 be area of semicircle. So this semicircle should be the big one. So semicircle, I can represent it by 1/2. And lastly, we need to get area of the small semicircle. We can call it 3 as area of small semicircle. And of course, the A should be the area of the shaded region. Now, after defining this, we need to have some plan here. For us to be able to get the area of this shaded region, then we have to subtract the area of the two geometries, that is the semicircle, small and big, away from the area of this quarter cycle. So we can have here, that is A1 minus A2, also minus A3. So let's start with getting area of A1 from here, and we have A1 is got by, since it is quarter cycle, the center degree here is 90 over 360, making a quarter, and that is where the name comes from. So we have quarter pi r square. Now after that we can make substitution, because we know the radius of this quarter cycle is 8. So we can have here A1 equals 1/4 pi times 8 centimeter, also times 8 centimeter, and that is the meaning of this square here. Now we can go ahead and reduce this by 4 to 1, so 8 by 4 we get 2, and if we multiply this 2 by this 8 we'll get 16. So we have here 16 pi centimeter square as the area of the whole geometry, and we can move on to get the area of the big semicircle, and from the word semicircle it must be 1/2 as we have defined here. So we have the area of a semicircle is given by pi r square half. And where is this half coming from? Is from here. This is also a straight line with 180. So 180 over the center degrees. If we are to complete this as a complete circle, then we shall get here that 180 by 360 will give us the half. So now what we need to know is the radius here. So the radius is the distance from here up to here. So we just need to divide this 8 by 2 to have 4 centimeter as the radius of this big semicircle. Now we can make substitution in our formula here, such that we have 1/2 times pi times our radius, that is 4 centimeter, times also 4 centimeter, since we have it here squared, and we can move on and also cancel these 2 with 4 to 2, and if we multiply 2 and 4, we get 8 as the area of the second geometry here. Now this is also in centimeter square. And the next thing here is to get the third area, and that is the area of the small semicircle. But then when you look at this small circle, you realize that we really don't know the radius of this, neither do we know the diameter. So we start to reason out how to do that. Now since we don't know, we can let this one to be r as the radius, and this radius will be the distance from here up to here. So we can indicate it as the distance from here up to here. Now, so since we don't know here, also there's an important point here that can help us to get the distance. And remember, from here to here is also another radius. Also, when we connect this to this point, then we can know also that this is 4 is the radius for the big semicircle. So let's go ahead and join those points together, like here, and adjust. Okay, so you can see that this one is a straight line, and somebody will argue how, if you have a circle like this, and we have center, and perhaps you draw some line, and we know that this line is radius, so this line will meet a tangent at 90 degrees. So if this is our tangent at 90 degrees, meeting this radius, if we have another radius here also joined together, this will be also at 90. Now since we have 90 plus 90, that is 180, then this must be a straight line. Now we can go ahead and get this hypotenuse, because we can see that the distance from here is 4 centimeter, and this one will be the same as our r. So r plus 4 will give us the distance here, and this distance, of course, is the hypotenuse to our right angle triangle here. So what we can do is to also find the distance from here up to here, and what we know here is that the radius is 8 for the quarter circles. When you subtract this r away from the radius of the quarter circle, we shall be left with only this side here, which is the height of our right angle triangle. So by doing so, we'll have here 8 minus r to give us this radius here, of course, in centimeter, and that is the distance from here up to down here. Now, using Pythagoras theorem, we will be able to get the value for r, which we can use that r to calculate the area of that small semicircle. Now let's go ahead and implement that. So before we implement, we can rename a few parameters here, and we can call this one here to be C1 as the center of the quarter circle, and let's call this one here to be C2 as the center of the big semicircle, and let's call this one here to be C3 as the center of the small semicircle. So having known these centers, then we can go ahead and calculate the value for r using Pythagoras theorem. So the Pythagoras theorem states that this length C1 and C2, when we square it and we add it to the length here, which is the height, and that is C1 to C3. square, we'll be able to get this length here, which is the hypotenuse, and C2 and C3 also square. So from there, we'll be able to substitute C1, C2 is 4 square plus C1 and C3 is what we have here, and that is 8 minus R, also will square. This must give us C2, C3, which is 4 plus R, and also we square. Now let's make this expansion, and we have 4 square is 16. Now we can use shorthand for the expansion here, where we expand the first term. We have here 64. 2 times 8 is 16 times negative R, so we have negative 16 R, and we square the last term. Negative R square, we get positive R square. Now on this side, we do the same thing. The first term being squared to 16, so plus 8 R, and the last one is R square. Now something looks like quadratic equation, but when you check it carefully, you realize that these parameters are the same, so we can go ahead and cancel them, because if you take to one of the sides, either to the right hand side or the left hand side, they will just simply cancel out. Now we also have 16 that is the same in both sides, so they can cancel, and we can simplify the remaining one here. So we have 64 minus 16 R equals 8 R. So we can take this to the other side. We have 64 equals 8 R plus 16 R. So if we sum this together, we'll have 24 R. So getting the value for R, we have here 24 is being divided on both sides here. So this one cancels, and the value for R is 64 over 24. When you divide 24 by 8, we get 3, and if you get this divided by 8, 64, we get also here 8, meaning R is equivalent to 8 over 3. So, and that is also in centimeters. So since we've already gotten our value of R, we can now go ahead and get the area of the small semicircle from the formula. A3 is given by 1/2 pi R square. So we can make our substitution where we have our pi remaining the same, and our radius here is 8 over 3, and we can square it. So when you square by distributing this power to the numerator 8, we'll get here 64 over 9. And we can see that 2 can divide this numerator to 32. Now from there, we can maintain this fraction just like that, and we have our area 3 is the same as 32 over 9 pi, and that is in centimeter square. So from there, we can now go on to substitute our formula we have driven earlier on, and that is area of the studied region was given by A from our definition here. So this is equivalent to A1 minus A2 minus A3. And our A1 is 16 pi. Also A2 is 8 pi. And A3 is what we had down here. That is 32 over 9 pi. So let's combine everything together and we obtain our final results. So we can make it here and say, therefore, the area of the shaded region from what we have written earlier on as A1 minus A2 minus A3 is now, so let's make the substitution where we had here 16 pi minus 8 pi minus our 32 over 9 pi, and remember everything here is having the same unit as square centimeter. So if we subtract this, we'll get the first two, get 8 pi minus 32 over 9. Now maybe you can go ahead and solve this one here, combining it to one number, and this is over 1. So we can get some LCM where A is given by, so let's get some more space here. The common denominator is 9, such that 9 divided by 1 is 9, and 9 times 8 is 72. So minus 9 divided by 9 is 1. So 1 times 32, we also get 32. And remember there's also pi here. So we can subtract this away, and we have our area as the 2 will subtract to 0, and 7 minus 3, that is 40. So we have here 40 over 9, and we attach our pi here. So together with our unit square centimeter, I think we can be consistent by putting our units also here. So with all this, that becomes our solution for this number, and that is the area of the studied region. So the only tricky part in this working here is the fact that we need to identify this relationship between this bigger semicircle and the smaller semicircle, such that we can be able to use Pythagoras theorem to find out the radius of the small semicircle, and with all that, we shall be able to just get our working so easily. So thank you very much for watching up to this time. See you in the next video. Peace out.